Now, finding the domain and range of multivariable functions is in some respects similar to finding the domain and range of single variable functions, but there are some notable differences. And so I want to go over the overview of what some of those differences are before we get into some of the specifics. So to begin with, the domain of a multivariable function depends on more than one variable. So we can no longer really express our domain and range in terms of a single interval, the way that we were able to in a single variable function. So the way that we have to express our domain is going to be in set notation. And so typically the set notation will end up looking something like this, where we specify x and y as a pair, and then we include some condition on that expression of x and y. Now, sometimes it may be that there is in fact no condition and that it's any real number, that would be our quote unquote condition. In other cases, there will be some relationship between x and y that has to be satisfied for the condition to produce a real number as an output. So we'll look at some specific examples, but those conditions will come from the specific equation that we're dealing with. But again, typically there will often be a relationship between x and y. If there are multiple conditions, maybe a condition on x and a condition on y separately, you would simply list them in combination in this statement. So this would be our domain. Now, fortunately, the range is still only producing a single output, so this can be expressed in interval notation, since there's only one variable that we have to deal with. Now, we're going to basically make a comparison between our multivariable function and the one variable function as we go about doing these examples. So think about your basic functions in one variable. We have polynomial functions where the domain is all real numbers, or where the range may be either some minimum value or some maximum value to one of the infinities, or maybe all real numbers, depending on the power of the leading term. We have square root expressions where we can't put anything negative under the square root. We might have rational functions where we can't put things that make the denominator 0 into the function. We might have log expressions that are similar to radicals, but that they don't take 0 as a value, so that the endpoint is excluded. So again, think about those kinds of typical one variable functions as we go through this. So let's consider f of x, y is equal to, let's start out with, let's do log of 3x plus 2y minus 11. So what is the domain of this function? The domain is going to be, again, we have to put it in the set notation form. And the condition, remember that for log, it's log of something. And the domain in the one variable case, that something that's inside the log has to be greater than 0. Not greater than or equal to 0, but strictly greater than 0. So our condition here is basically that this expression must also be greater than 0. That's our requirement. We don't have a specific restriction on x. X can, in principle, be anything as long as the y value will compensate for it to make this expression greater than 0. Likewise, y can be anything as long as the x value that goes with it makes this expression greater than 0. So we don't have a specific interval in which we can say, oh yeah, x can be anything or y can be anything. In some sense, that's true, but they have to be paired with each other. So you can't put in, for instance, a negative value for x and a negative value for y. You could put in a negative value for x, but only if you had a sufficiently large positive value for y. So there is a relationship between how we choose X and how we choose Y that has to be satisfied by this condition. Now, of course, you can rearrange this. You could try to solve for Y in terms of X, or just put the constant on the other side of the equation. Algebraically equivalent statements to this are also fine. But it's whatever this outcome is inside of the log, then that has to be greater than 0, whatever the combination of X and Y are that you choose. Now for the range, since this is a linear expression, it can in principle take on any of the allowable values, bigger than all the way down to 0, but not quite 0, or to as large a value as you want. If you pick X and Y sufficiently large, you can make the entire expression as big as you'd like. So the range here is then going to be negative infinity to infinity, because that is the range of the log function. Even in one variable, if you put in the right values, very close to 0, you'll get closer to negative infinity. Very, very large values, you'll get closer to positive infinity. The range itself hasn't changed. So let's consider another example. And I should also note that similar procedures will work for 3 or 4 variable functions. The range will still be a single value, and the domain will have to be expressed in terms of this ordered pair or ordered triple or what have you, depending on how many variables there are, and whatever condition is necessary to make the log expression or the square root expression work. So let's think about arcsine of X over Y. What is the domain of the arcsine? Well, remember that the sine has a range of -1 to 1. And so the arcsine has that range as its domain. So we're bound between -1 and 1. And so when we write out our set notation, xy has to be, again, such that we are in between, and again, we can be equal to X over Y less than or equal to 1. So as long as this ratio X over Y is between -1 and 1, then we will get an expression out of this. What is the range for this function? Well, the outcome, the output of the arcsine are the unique values from the sine function. So it's not all real numbers like it would be for the sine. It's that set of unique values, a stretch of values on the X interval where we get a one-to-one function. It turns out to be negative pi over 2 to pi over 2. And that should be a negative. Negative pi over 2 to pi over 2. Let's try one more. So let's say we wanted to find f of xy is equal to the square root of 16 minus x squared minus y squared. What would our domain be? Well, for the square root function, the domain is going to be xy such that 16 minus x squared minus y squared is greater than or equal to 0. And again, another way of putting that is that x squared plus y squared is less than or equal to 16. Again, just rearranging it. And in this case, I rewrote it because this actually gives us a hint about the range of our function. If we had a linear expression under the radical, then this radical could in principle take on any of the allowable values that you could put under the radical, so 0 to infinity. And so if this was just 16 minus x minus y, then you could always pick x and y to make that value as large as possible. But in this case, we're actually bound inside a circle in 2 dimensions. And the largest this value can take on is 16. The smallest that it can take on is, we could have these completely cancel out, and then it would be 0 under the radical. But the largest that this can take on would actually be when x and y are 0, and then we would just get the square root of 16. So the range here is actually going to be from 0 to 4. And again, this would be the same sort of consideration we had if this was simply 16 minus x squared, and we were simply dealing with a one variable case. There would be still a maximum value that this expression could be, and we would still have to account for that. Now, there are, of course, examples where the domain and range are all real numbers, and so we'll just close out with that kind of an example. If you have a polynomial example, then the domain is simply going to be all reals. And there's no relationship between them. X in R and Y in R. And then the range, this can go from negative infinity to infinity, and so that will swamp out whatever the other things are doing. So the range will then be negative infinity to infinity. So again, no restriction whatsoever. One other thing that you might want to consider as a last thought is, if you have multiple terms, then you want to find the expression, the set of values where all of the things are true at the same time. So maybe square root of y and trying to think of another example, maybe tangent of x plus y. So in this sort of an example, we can, in this term, we would say, okay, so x has to be greater than 0. X greater than 0. Also y greater than or equal to 0. But then also we have to deal with this tangent. And the tangent is not defined at odd multiples of pi over 2. So we would have to say x plus y not equal to odd multiples of pi over 2. So 2n plus 1 are the odd values. Pi over 2 is the multiples that we're doing. So this would be a very complex set of possible expressions for our domain. And because, you know, we could have x be strictly greater than 0, that's great. Y strictly greater than 0, that's great. So they don't really interact with each other. But here, not only do they interact with each other, but they have very specific individual values that have to be removed from the domain. So we have a very complex set of conditions on the domain. And then the range, we would have to think about if any one of these terms goes between negative infinity and infinity, then that will take over the whole thing. So even though y only goes from 0 to infinity, log will potentially go from negative infinity to infinity, and so will the tangent expression. So the range will therefore be negative infinity to infinity.